All right, guys, so here we are, our first official video of Unit 1. We are going to be talking about restricted domains today. So I'm going to give you some basics. We'll do one or two short problems, and then in class next time we will practice this skill to get really good at it. So as always, rewind, pause, rewatch the video, do what you have to do to get the hang of it. Fill out the Google form that goes with it afterwards, and then we will talk in class about questions you have and what we learned. Okay. So when we're dealing with functions this year, we're going to get into more different types of restrictions later, restrictions in trig functions, restrictions in logarithmic functions, restrictions in other types of functions. But right now we're just going to look at rational functions and radical functions. So we've kind of already talked about this when we were doing our equation solving from the first unit. But something you're probably just in the habit of and you've gotten used to is, in what cases will an x value result in an undefined y value? All right, undefined values show up whenever we divide by 0, right? So when we divide something, 4 divided by 2 basically says how many times can 2 fit into 4. But when we divide something by 0, it's saying how many times can 0 fit into 4. 0 never gets closer to 4. It's stuck. It never gets any little bit closer to fitting into that number 4. So that's why when we divide by 0, it gives us an undefined value. All right, so what we have to do to solve these, to find what the domain is restricted as, and maybe I'll put this here, this denominator cannot equal 0. The denominator cannot equal 0. To find the restricted values, we just basically set the denominator equal to 0 and solve. All right, and whatever values come out as our answer, those are the values that we can't let our function be. Okay? So a couple little examples. These are very straightforward. We can just look at this one, and basically we know x minus 4 cannot equal 0. So we saw we had 4 to both sides. We don't really have to do any math there, but we know x can't be 4. So our domain of this function, x such that, and then we have our interval notation that we talked about, negative infinity to 4. We just skip that one little spot, and then we go all the way up from 4 to infinity. So there's our domain. And then we can do the same thing here. X squared plus 2x plus 1 equals 0. Now we have a quadratic, so hopefully it can factor. If it can't, then we'll use the quadratic formula or whatever. But this is a nice factorable. X plus 1 equals 0. So this is actually the case. If we were to graph this, there's only one root, right? This is x equals negative 1. I guess we should have this, right? I don't really care how you do it, if you have a not equal to or equal to, but this parabola would just hit the x-axis once, right at negative 1. That's a little messy, but that's okay. And that's our domain restriction. So we would say x, the domain of this function is negative infinity to negative 1, or union, right? Could be either one, or negative 1 through infinity. All right, so that's our first domain restriction. We cannot let the denominator equal 0. Okay, the next thing. In what cases will an x value result in a non-real y value? So non-real is our key there. When we're talking about these domains, we're looking at the real number domain. So if you remember all your symbols, the real number domain, negative infinity through positive infinity. Non-real numbers show up when the radicand, the stuff under a radical, and I guess I'll just write it like this, is less than or equal, sorry, not less than or equal to, is less than 0. So the stuff under the radical is less than 0. That's when we get a non-real answer. So we can still have imaginaries. You guys learned a way around that last year. You still can have imaginary numbers, but those numbers are not in our real number domain. So for graphing purposes, for equation solving purposes right now, there's our real number domain. Okay, the x and the y-axis. The radical function, the square root of x, looks like this. Hopefully you remember that from years past. So you can see right there, the domain never goes negative here. It starts at 0, but everything is positive. Okay, now next year, calculus, maybe actually in Calc 3, multivariable calculus, we're actually going to see another axis, which is pretty cool. You're going to see a 3-dimensional grid. You're going to see the z-axis. So you have the x, the y, and the z, which is kind of coming straight up and down from there. It's like a three-dimensional picture. So that's where you're going to start seeing imaginary numbers that can get plotted on the graph. The z-axis is for imaginary numbers. But for now, we're just dealing with the real number domain, and that's why we have to restrict our domain for square roots. So new word there, radicand. Well, maybe not new, but it's the stuff under the radical. So to find the restricted values, so I guess to find what does work, maybe I worded that funny, but we're just going to set the stuff under the radical greater than or equal to 0 and see what we come out with. All right, so we'll do one or two of these. Same thing, we're starting really basic. We don't even really need to show any work here, but for this first function, what I would do is say, okay, for this to work, I need to set x minus 5 to be greater than or equal to 0. We can also think about this as a shift right 5. If you think about your transformations, we're going to talk about that a ton this year. We add 5 to both sides, so we know for this function to work, for it to be all real numbers in our domain, we know that the values, the x values, have to be greater than or equal to 5. So my domain would look like this: greater than or equal to, closed kind of hard bracket there, 5 through infinity. All right, so I'm going to pause and let you guys kind of start on this one. I'm going to solve it on my own. And there's a reason I want to do this one as well. So it looks like right away we're not able to factor this. And if you remember back to the last little mini review unit, what we did for questions like this was we kind of thought about this as an equal sign, right? And we wanted to find the critical values, those turning points. So what I want you guys to do is work through this, find the critical values, and then I'll give you some strategies about how to work with them. Okay? So go ahead and pause while I pause mine, and we'll get back together. All right, so little quadratic formula, completing the square if you want, and we get this value right here. So those are our critical points. But now we need to figure out where this graph is actually positive and where it's negative. And that's hard to do with that radical 37 there. So, I mean, you can punch this into your calculator. We don't really need it. The square root of 37 is right about 6. So if I do 5 plus 6-ish, 5 plus 6 is 11. 11 divided by 2 is 5.5. So that's roughly one number on my graph. 5 minus 6 is negative 1. Negative 1 divided by 2 is roughly negative 0.5. So those are my two critical values, my two turning points. But remember, we need to think when this graph is positive. So if I look back at what we have here originally, x squared minus 5x minus 3. That's a quadratic function. It's a parabola. The a value is 1, so it opens upwards. So my graph is going to look something like this. And this is the stuff we did last unit. So I know in order to make this positive, those are the parts of the graph that I need to include in my domain. So to put it all together, the domain of this function that makes the stuff under the radical positive is negative infinity all the way up to 5 minus radical 37 over 2. I might run out of room here. Or, can I drag this? Yes, nice. Or from here, which is 5 plus radical 37 over 2, all the way up until infinity. And I just realized I made a mistake. Did you guys catch my mistake? 0 is okay here. So I had this greater than or equal to 0. So I need to make these the inclusive brackets. Hopefully you guys caught that. My bad. There we go. Okay? So that domain will satisfy, will make sure all of our outputs are real numbers. All right, one last thing before we're done. Now, what if it's a combo platter? What if both things happen? So if the square root is in the denominator, we combine the two rules. All right, we set the radicand to be greater than 0, not greater than or equal to. Okay, so if I look at this first example and I see what's happening here, there's two things going on. I have a radical, so I know this can't be negative, but it's also in the denominator, so it can't be 0. So we have two options. Rationalizing this, sure, we could do that. The reason we rationalize is to get a constant, like a radical 7 out of the denominator. If this is just a function we're dealing with, there's no need to rationalize this. It doesn't really get us anywhere. It doesn't help us out at all. So I guess long story short, we need to combine our two rules here. So since it's in the denominator, we know it can't be 0. But it's also under a radical, so we know it has to be greater than or equal to 0. So if we kind of look at these together, the only way this all works out is if that 2x minus 9 is just plain old greater than 0. Okay, so we'll solve that. You can see pretty quickly we would get x greater than 9/2, and that is our domain, x greater than 9/2. So 9/2 all the way up through infinity. Okay, let's not worry about this one. This is kind of the same one we just did. We would just need to change the greater than or equal to just a plain old greater than. All right, and we would solve that out. Notice here, I put this in here to throw you off a little bit. That 2x in the numerator, don't overthink this. There are no restrictions there on that 2x part of it. All right, don't just start throwing things. I can't let that be 0. I have to make that positive. Think to yourself, is there anything that I can't let x be in the numerator? Can x be 0? Sure, right? 0 divided by anything is okay. It's just 0. X can be negative, x can be positive, x can be a fraction, and x can be anything. There's no restrictions for this part of it because there's no square root, right? There's nothing that we need to worry about. It's just the denominator in this case. We need to make sure it's not 0. We also need to make sure it's not negative. So that one I think is factorable. If you want to solve that one out, you can. I want to put it all together here, and then we'll get to the practice in class. So we have a ton of practice examples, but let's look at this one here. We have two situations happening. So I'm going to let you solve this out. Find your domains, find the stuff that you know has to work. And then I want to give you a couple strategies of how to put it all together. So I'm going to pause and I'm going to solve these two pieces out. And then I want you to unpause and I'll walk you through the last couple steps here. Okay, so pretty straightforward. Those are your two domains, x less than or equal to 4 and x cannot be 3. So you can look below. We're going to get into some pretty complicated, well, not complicated. We're going to get into some domain restrictions that have a lot more going on, a lot more pieces. So here's what I would suggest. Always kind of break it up into sections. Look at each section differently, right? Look at those terms. If you look down at the practice for number 1, there's no reason to distribute all this stuff and to multiply all this together. It doesn't get us anywhere. We want this to be factored in as simple as possible. So break each chunk into its own sections like I did here. So like there's section 1, there's section 2 is what I mean by that. Then let's put them on their own number lines and try to line it up. So I'll show you what I mean by that. So like if here's 0, roughly, there's 0. My first domain, I knew x had to be less than or equal to 4. So there's 4. For this domain to work, I know x has to be less than or equal to 4. So there's my shaded arrow that way. The next one, I know x can't be 3. So I'm going to put 3. I'm going to try to line it up where it would be below 4. I'm going to try to overlay this. So here, everything's fine. Both directions from 3. So now the trick for these questions is our final answer, our domain restriction, it has to work for everything. So if I look at these two number lines, I have to give my final answer. I have to give my domain restriction so that it works for both parts of this. So what I think about is, I think like I'm playing like original Super Mario Brothers, like the old school Nintendo game where you can only walk left to right. So if I'm Mario here and I'm walking left to right, my domain works here. It works for everything. It's working. Both values are shaded yellow. And then all of a sudden I get to 3 and I have to stop. I can't use 3 in my domain because it would make the denominator equal to 0. So I know I have to pause at 3 and then I keep walking, and then boom, I hit another stopping point at 4. So 3 I have to stop, 4 I have to stop. But if I keep walking here, this part of the domain doesn't work. All right, so as soon as something doesn't work for part of my function, it's out the window. It can't work for any of it, right? So I can't say, well, the number 10 works for some of it, but it doesn't work for this part of it, so I'm just going to put it in there anyway. If something doesn't work for part of your domain, the whole function doesn't work. So I hope that makes sense. We're going to talk about that a lot in class. So my final answer, where can Mario walk? He starts at negative infinity. He can go all the way up to 3. He has to take a little break there. He picks up just on the other side of 3. but then he has to stop. End of story at 4. He can't go past 4 because that makes the numerator imaginary, and we can't let that happen. So there's my final answer. All right, so we'll practice a lot of these in class. If you have any questions, bring them to class, talk about them in our Zoom, talk to your learning group members. That's all. Get to the Google form, and I will see you guys next time. Bye.